Hello, and welcome back to another lesson in AP Statistics. Today we'll be finishing up Chapter 5, which will be expanding on our probability rules, and we'll learn some new formulas that have to deal with conditional probability and independence. So when we're talking about conditional probability, we're looking at the probability that an event occurs given that a different event already happened. For example, if I am rolling two die, right, I have two different dice, two die, and I say, what is the probability of rolling a sum of a 7 given that I already rolled one die and it says 3? So the condition is I already have one die that says 3. So what's the probability that the other die I roll adds together to get a 7? This is called a conditional probability, and it's written as the probability of B. This vertical line is read as given, so it's B given A. Okay, so vertical line means given. You might also see it as A given B. So the formula for probability of A given B or probability of B given A, we'll use the top formula first. This is a formula that you will see on your formula sheet that I'll show you in a second. Excuse me, I have the hiccups while I'm making this. I don't know why I have the hiccups, but I do. Anyway, the probability of A given B is the probability of A and B divided by the probability of B. Now, this symbol means intersect. We use the term and for intersect. So this is a formula that you will see on your formula sheet. Where can you find your formula sheet? Well, if you go to our AP Stat page, you'll see a formula sheet right here. And you'll see this is the formula sheet that you can use on the AP exam. And you'll see on the first page, you have the probability and distributions formulas. This formula right here we saw in section 5.2, which is a probability of A or B. And this is assuming that there is intersection, which is why you subtract the intersection. Over here, we have the probability of A given B, and this is the formula that we're looking at right this second. Okay, so you can find those formulas on your formula sheet. Okay, so let's go ahead and use these formulas. So here I have a two-way table. When I have a two-way table, I don't have to use the formula, and I'm going to show you both ways. One, how you could use the formula and how you could not use the formula. So we're going to let event E be that the grade comes from an EPS course. EPS meaning engineering and physical science. So it comes from one of these courses. Event L, yeah, the grade is lower than a B. Okay, so the probability of event L, which means the probability of selecting someone and their grade is below a B. Well, the first thing we gotta do is we gotta find our totals. So we're gonna find our totals. Here they are. Okay, and now the probability that we select a student that has a grade lower than a B is going to be, well, below a B, 3,656 kids were below a B, and there were 10,000 total, so it will be 3,656 divided by 10,000. Now, the probability that event E given event L already occurred, meaning the probability that you select a student that where the grade comes from an EPS course, given that their grade is lower than a B. So now we're only looking at the students who got a grade below a B, which is a 3,656. How many of those came from the EPS courses? Well, 800. So you will see 800 divided by 3,656. Now that is a conditional probability where you did not have to use the formula, because we have a two-way table. However, I will show you how we could use the formula if we wanted to. So here we are, same exact thing we have. And we want to find the probability of event E given event L. And according to our formula, it would be the probability of event E and event L over the probability of event L. Well, the probability of event E and L, so that would mean comes from an EPS course and below a B, would be 800 divided by 10,000. So it would be 800 divided by 10,000. Divided by the probability of event L, which we actually found in the first problem. When the probability of event L is the probability of getting a student below a B, which is 3656 over the 10,000. And when you do this, you will see that the 10,000s will cancel out, and I'm left with 800 over 3656. So I could use the formula here, which I showed you, and you would get the exact same answer that you see here, where I didn't actually use the formula. So if I have a two-way table, you certainly don't have to use the formula, but you could if you wanted to. There are going to be times when that's the only option. On the flip side, if I am looking for the probability of event L given event E, that would be the probability that the student got below a B, given that they came from an EPS course. Now I'm just looking at people in an EPS course, which is the 1,600 total, and the probability that they got below a B would be the 800 out of 1,600. So half of the students in an EPS course got below a B. Okay, those are conditional probabilities. Then we have this general multiplication rule. You actually don't get this on your formula sheet. The probability of event A and event B occurring, so intersecting, is the probability of event A multiplied by the probability of event B, given that A already happened, right? And this should make sense because if we're talking about two independent events, then you can multiply the two independent events together because they shouldn't affect one another. And what you'll notice is that the conditional probability here, the probability of event B given event A, if event A doesn't affect event B, then this multiplication rule just becomes the probability of A times the probability of B. And I'll show that in a little bit when we're doing proving that rule. So this is assuming that event A and B are not independent. Okay. It's easier when we're dealing with probability sometimes to use a tree diagram when figuring out a sample space and then using that to find your probability. For example, if I'm flipping a coin twice, so 2 coins, my first toss, I have 2 options, heads or tails. Okay. My second toss, I have 2 options, heads or tails. Which means that my sample space, I'm flipping 2 coins, is going to be either I get a heads and a heads and a tails, so I'm just following the tree, or a tails and a heads, or a tails and a tails. So my sample space is heads, 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 tails, tails, heads, tails, tails. And I found that by just following the tree, following each branch on a tree. So the probability of getting 2 heads would be 1/4. Or you could think of it as 1/2 times 1/2 is 1/4. Or you could think of it as 1 divided by the sample space, which is 4. Okay, so my tree diagram has probabilities on it because there's a 50% chance of a heads and a 50% chance of a tails. Okay, so let's look at this example. The Pew Internet and American Life Project finds that 93% of teenagers use the internet and that 55% of online teens have posted a profile on a social networking site. The question is, what percent of teens are online and have posted a profile? So we are going to make a tree diagram. So if I have a teenager, they are either online or they're not online, which means that 93% of them are online and 7% of them are not online. That's this number here, 93%. So 93% are a yes, 7% are a no. If they're online, then 55% of those people online have profiles. 45% of the people online do not have profiles. That's this number here, the 55% of the online teens. Whereas if they're not online, then 0% have a profile, and 100% do not have a profile. So what percent of teens are online and have posted a profile? So I'm looking for teens that are online and have a profile, which would be this tree branch right here. So it'll be 0.93 times 0.55, because it'd be the probability of event A times the probability of event B, given that A already happened. And that's our probability of A and B is the probability of A multiplied by the probability of B given A. And that is this tree branch right here. So the probability of that occurring is 51.15% of teens are online and have posted a profile. Conditional probability changes when we say that two events are independent. Independent is different than mutually exclusive. Mutually exclusive, we talked about how mutually exclusive events cannot happen at the same time, but they're not independent. Independent events are events that don't affect one another. For example, let me think of one. The probability of it raining, the event of raining tomorrow, and the event of, me waking up. Those two events are independent. The fact that it's going to rain tomorrow does not affect the fact that I am probably going to wake up. Okay. Unless something happens to me. So those two events are independent of one another. So independent events, if they're independent events, then the probability of A given B is just the probability of A, because this condition B doesn't affect A. Right? If the probability of me waking up tomorrow is 99%, and I said, hey, what's the probability that you wake up tomorrow given that it's raining? Well, it's still 99%, because the weather does not affect whether I'm going to wake up tomorrow or not. And vice versa. The probability of B given A is just the probability of B, because A doesn't affect B if the two events are independent. Okay? Which means that the probability of A and B occurring is just the probability of A multiplied by the probability of B. Because our original formula, this was the probability of B given A, but the probability of B given A is just the probability of B. So now the multiplication rule for independent events is a little bit different than the multiplication rule for non-independent events. For example, well, way before your time, there was a space shuttle called the Challenger, and it was an absolute disaster with it. Okay, it was determined that the failure of the O-ring joints in the shuttle's booster rockets were to blame for it exploding. Under the cold conditions, it was estimated that an individual O-ring would function properly 0.977 of the time. Okay, so 97.7% chance or probability that the individual O-ring would work. The issue with this is that each O-ring succeeded or failed independently, which means if one of them failed, the whole thing exploded. So what is the probability that all 6 of these work properly? Well, that would mean that you would need the probability that joint 1 was good, the probability that joint 2 was good, the probability that joint 3 and 4 and 5 and 6 are all good. So you need a success, a success, a success, a success, a success, and a success. You need 6 successes. So while 97.7% seems high for one individual O-ring joint, which is probably what they were thinking about, the probability that they all succeed is not as high as you would think. So the probability that they are all succeeding would be 0.977 times 0.977 times 0.977 and so forth, which means that the probability that this space shuttle was going to successfully take off was only 87%. There was a 13% chance of this space shuttle blowing up during takeoff. And that should seem extremely high because it is. Okay, and that's why this was such a disaster, because some engineer thought that this was a good idea, but it was not. Nowadays, they have special backup O-rings that work independently of the original O-ring, but they don't all have to succeed. Like if the first one fails, the second one can still succeed, and it would still be okay. So that way disasters like this don't happen. And these events are independent, so we were able to just multiply their probabilities together. Okay. That's it. We'll see you guys in class.